talking about BDM, business decision making, decision making, right? Here's a question for you guys: what decision you make? So we all want to protect endangered species, right? Endangered stuff. What if you see an endangered animal eating some endangered plant? What would you do? Very important, just in case you encounter such situation. Oh no! I told you this is. My dad gave me this. Okay, so let's let's try to be sensitive still. So we have a number of things to cover. Sometimes you may have a new constraint, right? Or sometimes you may delete a constraint, right? How will that change your optimal solution? So here is deleting a non-binding constraint. So what we do is, this is a constraint which is not binding, right? What if we delete it? So this constraint says has to be R plus C has to be 300 or more, right? That's why it's this way, right? But now if you remove it, if you remove this constraint, then this one disappear, right? Then this becomes the new feasible region. And what happens? Does that change the optimal solution? No, still here, right? So does it change the OFV? No. And how about you delete a binding constraint? Okay, so let's see which one we want to delete. How about this one? Okay, so this constraint is what? This is the proportion constraint. Okay, so I want to delete this one. Then you have something like this. Used to be a line here, right? Used to be a line here. Now that line is gone, so this becomes the feasible region. So because of the new feasible region, right? So of course the region is going to be bigger, right? It's here, there, over here, right? And then this point is not going to be optimal anymore, right? Because this is the objection function line. And you can move this line even further away from zero. You will touch this point, right? When the objective function line touches this point, it's going to be the optimal, right? So this is the new optimal. So this tells us if you delete a binding constraint, optimal solution very likely is going to change, right? And of course, graphically speaking, we know this is the new optimal, and you can also find the new OFV. And in reality, you have to resolve it to figure it out, okay? So here is the kind of summary, right? If you delete a constraint, it depends on if it's binding or not. If it's not binding, nothing changes, right? If it's binding, everything changes. So what if you add a constraint? You add a constraint. So this is what we had, right? And this particular line, if you remember, is R minus C, right? And let me double check. This constraint is R minus C larger than or equal to 200. Now, if I add a new constraint, which says R minus C is less than or equal to 500, okay? So this is the new constraint, and then the feasible region is going to be changed, right? But this change, as you can tell, this addition of the new constraint will not change the optimal solution. Okay, graphically speaking, this is still the last point the objective function line is going to touch, right? And why is that? Because the optimal solution, 600, 400, at the original optimal solution, this new constraint is going to hold. Okay, so this is the original optimal solution, right? So 600, if you plug in these numbers here, right? So 600 minus 400, of course, is less than 500. So this new constraint is satisfied automatically at the original optimal solution. So nothing changes. Okay. Of course, another possibility is that how about the new constraint you add actually cannot be satisfied at the original optimal solution. Okay? If that's the case, for example, if that is the new constraint, then you are saying that you have to go to the other side, right? So that's new feasible region. This original optimal is actually not feasible at all, right? So of course, the optimal solution is going to change. Okay, so adding a new constraint, you just want to check if the new constraint is satisfied at the original optimal or not. Okay. And the next one we want to, think about is what if the left-hand side of constraints will change? The left-hand side, okay? So that means sometimes if you add variables, of course, the left-hand side will be changed, right? So here is the simple result, okay? So if we change the left-hand side of any constraint, okay, the sensitivity report we get from Excel solver will be useless. Okay? So if you change the left-hand side of any constraint, you have to resolve the whole LP to figure out the new solution and the new optimal objective function value. Okay? So there's one implication, right? If you add or delete a new variable, of course you're going to change the left-hand side. Because if you add a variable, say y, then on the left-hand side you have to do the plus y or minus y thing, right? So if you add or delete a new variable, you have to resolve the whole problem. Okay? Okay, so now we want to talk about the next big thing, which is what if you have changes in the objective function coefficients? Okay? So let's check. Again, this is the optimal, this is the original problem, right? We have the original feasible region, we have the original optimal solution, we have the original OFV, right? And that is the original objective function, right? So 5 and 12, those are the coefficients of objective function, right? So let's focus on this particular coefficient 5, okay? What if this number is going to increase? So instead of 5, how about now it's 6? Okay, used to be 5, now it's 6. Will that change the optimal solution and the optimal OFV? So how do we do that? So let's try to use the objective function value, objective function line method, right? So we know that if you change the coefficients here, you are changing the slope. You are changing the slope, right? So for the original problem, it is the slope is 5/12. Okay. So it's this. If you make it 6, right? Then the slope is going to be minus 6/12, right? So this is 5/12. When you have 6/12, it's basically going to be steeper, right? It's going to be steeper going to that direction, okay? Now, whether the new objective function line is steeper than this one or not, you have to also, remember or figure out what is the slope of this constraint, right? So let's go back. So this line, it is the packing, which is R plus 1.5C less than equal to 1800. So that is the line. What is the slope? Yes? That's correct. So negative 2/3, or let me say it is 8/12. It is? Yes. Lost again. So if you make it, 6, right? And this becomes minus 6/12, the slope, right? Is still going to be less than, it's still going to be flatter than this one, right? So if you move this one to 6, it's somewhere here, okay? If you move 7, still here. But if you move 8, then the objective function line is going to overlap with the constraint here, right? So let's see. So when it's 6, you move closer to this packing line, okay? You make it 7, closer. If it's 7, right, the slope is minus 7/12, which is closer to minus 8/12, which is the slope of this red line, right? But at here, up to this point, right, the optimal solution stay the same, right? Stay the same. So the optimal OFV is going to change. Okay? So the optimal solution will be the same as we can see from the picture, right? Why the optimal OFV is going to change? Yes?
The coefficient will change.
That's right. I mean, obviously, if R and C stay the same, but you change the coefficients, then the value of the objective function is going to change, right? As we said, if you change this number from 5 to 8, right, then these two lines is going to be overlap. When it is overlap, as we said before, every point at this line segment is going to be optimal. So every point on this line segment will be optimal, right? So again, you can tell that you can change the value up to a limit, right? Beyond that, maybe the optimal solution is going to change. Maybe the objective function value is going to change, right? And just give you one example, right? If you change the number from 5 to 9, from 5 to 9, right? Then this line, objective function line, is going to be steeper than this line, right? Than this line. In that case, okay, so tell me when this becomes 9, which point is optimal point? What do you think? I'm not sure. So we have like 5 corner points, right? So which one is optimal? It's like a multiple choice question, A, B, C, D, E, right? If you just randomly guess, you have 20% of winning chance. So your hands, do you? Wallace?
500.
So which point is the optimal? Or you can tell me the coordinates.
C.
C? Which one is C?
The 600 point.
Here?
Yeah.
Incorrect. So now you have four, four more options. Which one you choose? So 1, 2, 3, 4. Which one?
The fourth one.
Correct. Yes. So the second time is the charm for you.
Thanks.
Okay, so because if this is the objective function line, right? You try to move away from 0 as much as you can. Of course, you move to here, right? This will be the last point you touch. Okay. Excellent. So, for this one, the optimal solution is going to change. So again, as we said, that there's a range. Beyond that, the optimal solution is going to change. So when we talk about the objective function coefficient change, we have something called the range of optimality. All right. So this is the range of the coefficient values where the original or the current optimal solution will stay the same. Okay. Of course, although the optimal solution will be the same, the OFV is going to change because you change the coefficients, right? So Excel solver is going to give you such a report, okay? So this report, this table is variable cells. You have the decision variable 1, decision variable 2. Those are the final values. So this means an optimal solution. In the optimal solution, first variable is 600, the second variable is 400, okay? And those are the objective function coefficient, 5, 12 in the original problem, and those are the range of optimality. So you can increase this coefficient 5 by 3. So this number can be increased to 8 without changing the optimal solution. This number can be decreased by 17 without changing the optimal solution. Okay? Okay, so but there is like a trick. There's a trick. Okay, so when we talk about the range of optimality, okay, we are talking about the decision variables, right? The coefficients of the decision variables. But there are two types of variables. If we talk about sensitivity analysis, when we talk about the range of optimality, that is, some variables are basic, some variables are not basic. So basic means the variable is not 0 at optimality. If the variable is 0 at optimality, that means it's a non-basic variable. Okay? So how a change in coefficient will change the optimal solution depends on the type of variables it is. Okay, so let's check it out. So in our example here, right? So the final value 600, 400. That means in optimality, both variables are non-zero, so they are basic variables, right? What if some variables are not basic, are non-basic? Okay, so of course we have to change the parameters a little bit. Try to find, the situation where we have a non-basic variable. So suppose we change the original problem, right? So here used to be 12, now it's C, right? This used to be 1200. Sorry, it's 1000, I believe. It's 1000, now it's 1300. Okay. Anyways, that's you can think of it as a new problem, right? And you solve it, you will find out the final value, those two. So as we said, if at optimality the final value is not zero, so this is the basic variable, right? And this is a non-basic variable. And then we have the range of optimality, right? Or we have the range of optimality. So it's, well, so if I tell you it's interesting, probably don't believe me, but if you look at those kind of problems, right, it's a maximization problem, right? And those numbers, if you think about it, are like profit margins, right? Profit margins. Why, in optimality, you do not produce any catch-as-made? So here is something very shocking. Probably the profit margin is not high enough, right? So this is zero because this coefficient, which is like profit margin, is not high enough. It's not high enough. Okay. So the allowable decrease of this number is infinite. Okay? At profit margin of 4 per unit, you don't produce anything. Okay? If you decrease it to minus infinity, of course you're not going to produce anything as well, right? So you can decrease the number as much as you want, the final value will be the same. It's still going to be 0, right? But if you increase this one by 1, so 4, right? What if it's 5? The profit margin is higher. Do you have sensitive to produce some of those products? Maybe, maybe not. Okay? But here it tells you that you have to increase this profit margin by at least 3.5. If the increase is within 3.5, then the profit margin is going to be still low, okay? And then the final value is going to be still 0. Okay? So this range of optimality means within this range, the final value is going to be stay at 0. Stay at 0. In other words, if the profit margin is increased by 3.5 or more, then this number will become non-zero. Okay? Does it make sense? For non-basic variable, the range of optimality is the range where the optimum value stays at 0. Okay, if we want to like summarize things, then we can say that to see a change in objective function coefficient, depends on if the variable is basic or non-basic. If it's non-basic, then within the range of optimality, the optimal solution will not change, and the OFV will not change. So why the OFV will not change? So even if you change the, coefficient, yes.
Because the coefficients are changing?
Hmm?
Because the coefficients are not changing?
They are changing because if we change the objective function coefficient, yes.
In the example before, we decided we're not going to make the Catcher-Smith because the coefficient is too low, so it's not sufficient profit.
That's right.
So there's no point in making a.
That's right. So the OFV is not changing because they are non-basic variable. That means at optimality, the value is 0, right? If the value is 0, if you change the coefficient, you're not going to change anything, right? Now, if it's a basic variable, that means they have values, they have non-zero values. They have non-zero values, right? Now, if you do the change within the range of optimality, the range of optimality by definition is the range where the optimal solution will not change, okay? But the OFV is going to change because you change the objective function coefficient, and those optimal solutions are non-zero. Of course, the objective function value will change, okay? So outside the range of optimality, we don't have any results. Okay, just have to solve the whole problem, figure out the new things. Okay, so just like the range of feasibility, if your change is outside of the range, sorry, you have to do the whole thing over again. Okay, so something related, very related, is called reduced cost. So reduced cost is something very, strange. Okay, so you assume those objective function is like a cost function. Okay, you assume those coefficients, they are not profit margins, they are like cost parameters, cost, right? And how much cost you have to reduce, to make the variable basic. Okay, so again, it's a little bit tricky, but let me explain. Okay, so for example, for this variable, Catcher-Smith C, right? So remember the original. For this case, right, objective function we start with is what? Is 5R plus 4C, right? And as we know, the 4 is not high enough, so the profit margin 4 is not high enough, right? So at optimal is 0. You produce 0 Catcher-Smith. To make it non-zero, of course, you have to increase the profit margin, right? So here it says, if you increase the profit margin by 3.5, then this zero value is going to be non-zero. Okay, if you increase the profit by 3.5, then it starts to make sense to produce non-zero number of Catcher-Smiths. Okay. Now another perspective is in terms of cost. So this number is minus 3.5. What does it mean? It means you have to reduce this number by at least minus 3.5 before this value becomes non-zero. Okay? So if you reduce 4 by minus 3.5, So you're actually saying that if you increase this 4 by 3.5, okay? So this is a very strange name. It's called reduced cost, okay? So reduced cost indicates the amount you have to reduce from the coefficient before the variable becomes non-zero at optimality. Okay? So this makes sense. This term makes more sense when we are talking about cost minimization problem. When we talk about cost minimization problem, okay? When we talk about profit maximization problem, this term is kind of strange, but this is something provided by Excel solver, right? So let's look at this example. And again, this probably is a pretty simple example, so I'm going to skip. Let's skip the details. And you know, you have the decision variables, you have the objective function, you have the constraints, right? Then you can use solver to solve it, right? And then this is the report provided by Excel solver, okay? So here we can tell that we have, maybe let me ask you, do we have a non-basic variable here? Yes.
Chocolate?
Yes. So the chocolate is as chocolate what? Chocolate cake, okay? So this is a non-basic variable. The other two are basic, right? Because at optimal, the value is 0. And the objective coefficient is 32, right? Which means what? Means at this level, the profit margin is too low, so you don't produce anything, right? But if you increase the objective function by 3 or more, then it's going to make sense to produce non-zero chocolate cakes. Okay, that's why this is 3. That's why this is minus 3. So again, we are saying that if you reduce, you have to reduce this number by at least minus 3 before this becomes non-zero. In other words, you have to increase this by at least 3. And as you can see, we can actually like kind of summarize, and we can kind of use those rules, right? So first of all, for maximization problem, reduced cost is less than 0, less than equal to 0. Why? Because maximization problem is like a profit margins, right? When do you start to produce something? That's when the profit margin increases, right? Profit margin increases. In other words, you do that when the reduced cost is negative. Increase profit by a positive amount is the same thing as you reduce the profit margin by a negative amount, right? So, so it makes sense, right? Now we can also have a minimization problem, right? So minimization problem, suppose it's a plus 2b, then the 1 and 2, they are like a cost coefficient, right? So when the cost is too high, you don't produce anything, right? So when you reduce the cost by a certain amount, you have to reduce the cost by a positive amount before you start to make something, right? So that's why for minimization problem, reduced cost is positive. Okay? Also, the final value times the reduced cost is always 0. It's always 0. Why? if the final value is non-zero, that means the basic variable, right? That means you're producing something, some units of it, right? In that case, you don't have to reduce the profit margin, you don't have to produce anything before that variable becomes basic, because it's already basic, right? It's already basic. So when final value is not zero, this must be zero. So that would be zero, right? Now if the final value is zero, of course everything will be zero, right? So does it make sense? All right. So next one we're going to talk about probably the last major category of sensitivity analysis. What if you have multiple changes at the same time? Okay? You have multiple changes at the same time. So we're going to talk about two things. You know, when we talk about the multiple changes, right, that means it can be all kinds of situations, right? You have changes there, right? Which probably is too much to do. But let's just look at two special cases. The first one is you have multiple changes in the objective function coefficient at the same time. Then what do you do? We have two scenarios, okay? The first scenario is all the variables are not basic. That means those variables affected, they are zero at optimality, right? So if that's the case, you just have to check, you just have to see if the objective function coefficient, those affected coefficient are the changes, the change, is it within its range of optimality or not? In other words, if all the variables are non-basic, okay, although you have multiple changes, you can just treat it as individual changes. You want to make sure each individual change is within the range of optimality, all right? And in this case, if they are within the range of optimality, then the optimal solution will not change, then the OFV will not change. Okay, again, that's like by definition, right? Non-basic means they are always zero. If they are always zero, nothing is going to change. So the second scenario is at least one variable are basic. That means at least one variable are not zero. In this case, we have a rule called 100% rule, right? 100% rule. That means for this kind of situation, for this kind of scenario, you have to take all the changes, you have to consider all the changes at the same time. You cannot treat them as individual changes, okay? So how do we apply the 100% rule? For each change, you calculate the percentage of its allowable change. So there's a limit, you check in terms of that limit, what is the relative change, right? And then you look at the sum of all the percentages. If that sum is 100% or less, then the optimal solution will not change, okay? Of course, the OFV is going to change. If the sum is strictly larger than 100%, then the optimal solution will change, and you have to resolve the problem to find it out. Okay? So that is the 100% rule. And let's just do one example. So you have the report, right? And you can tell those two variables, the number of doors, the number of windows, 2 and 6. So both of them are basic, right? Basic variables. Now, if you change 300 to 5, and at the same time you change this to 350, then what is the new optimal solution? What is the new optimal OFV, right? So a number of things to check. First of all, you have to check what we are talking about. Are we talking about the changes in the coefficient, the objective function coefficient, or are we talking about the changes in the constraints, right? Of course, this is in objective function coefficients, okay? Second, you want to check if it's basic variables or not. So both of them are basic. Both of them are basic, right? That means you have to, so if this at least one basic, you have to apply the 100% rule, right? If two of them, both of them are basic, of course you have to apply the 100% rule as well. Okay? So let me just find out what is the change 1 is. So change 1 is increase by 225, right? So increase by 225. Of course, that is the absolute change, right? You have to find the percentage. So the allowable increase, the maximum is 450, so divided by 450, so that is 0.5. Change number 2. Number 2 is decreased by 150, right? So that is 150 divided by, so this is a decrease, right? So you have to do 150 divided by the allowable decrease, not here, but there, right? Which is 300. Okay, so you have two changes, they have to sum them up. The sum is 100%. Okay? Now, will the optimal solution change? Hmm? Okay, yes. That's right, it doesn't. Okay, because the rule says 100% or less, there's no change, right? If it's strictly larger than 100%, there will be change. Okay. So if I want to write down here, I would say optimal solution, no change. Still 2 and 6. Okay. Now, how about the objective function value? Well, that's very simple. You know, just 2 times the new coefficient plus 6 times the new coefficient, right? That would be the new OFV. So, any questions here? Okay, so this example I'm going to skip. Okay, I want you guys to solve it probably at the end of this class. Okay. Now let's talk about simultaneous multiple changes in the right-hand side of constraints. Okay. So when we talk about changes in right-hand side of constraints, remember we have to check, first of all, if the constraints are binding or not, right? If the constraints are not binding, then nothing is going to change. Nothing is going to change, right? Now, if at least one constraint is binding, if at least one is binding, you have to apply the 100% rule. So the rule is the same. It's very, very similar. Okay. So first of all, you have to calculate. For each change in constraint right hand side, you calculate percentage, right, of this allowable change. Then you look at the sum. Okay. If the sum is 1% or less, then the shadow price will be the same. So let me just remind you that within the range of optimality, the optimal solution will not change, right? Within the range of feasibility, the shadow price will not change. Okay? So the shadow price will not change, and how do you calculate OFV? It's old one plus the sum, because this is a shortcut to calculate the changes, right? Otherwise, if it's larger than, if it's strictly larger than 100%, you have to resolve the problem to find out. Okay? So let's look at examples. So look at the report. We basically have 3 plants, right? And we have constraints. And now we have changes, right? Suppose one available hour in plant 3 has been shifted to plant number 2. How will the optimal solution and OFV change? Okay, so just have to be careful here. So it used to be 18 and 12, right? And now you shift it, right? That means this one is decreased by 1, and this one is increased by 1. Okay? So first step, are those binding or non-binding? Binding. Both of them are binding, right? So both binding. So you have to apply 100% rule. Okay? So what I do is change 1. So change 1 is increased by 1. Okay? So the allowable increase is 6. So the percentage is 1 over 6, right? So change 1 is 1 over 6. And change 2. Change 2 is decreased by 1, right? So that's the decrease. So you look at the maximum allowable decrease is also 6. So percentage-wise is 1 over 6. Proportion-wise is 1 over 6, right? So the sum is 1 over 3, right? So 1 over 3, of course, is less than 1. So shadow price stay the same, right? Shadow price is the same. Shadow price is the same. So when you have changes to the right-hand side of binding constraints, okay, the optimal solution will always change. The objective function value will change too, right? But there's a shortcut, right? So we can find out what are the changes, what are the change in the OFV due to the changes of the right-hand side. So that is, the change 1 is you increase by 1, right? And within this range, the shadow price will be the same, right? So here increase by 1 times shadow price. The shadow price is the increase, shadow price is the value, is the change in objective function value for each increase of the right-hand side. So this is 1 times 150. And then for this one, right, you decrease by 1, okay? So this value means if you increase this one, if you increase 18 to 19, the OFV is going to increase by 100. Now you decrease by 1, of course, it is 100 times minus 1, right? Remember, shutter price is the change in OFV for every unit of increase in the right-hand side, okay? So the change in OFV will be 50, Any questions? So basically for this kind of sensitivity analysis, okay, which is very important for our course, you need to do practice problems, check things. First of all, is it range of optimality or range of feasibility, right? And then if it's binding or non-binding, or if it's basic or non-basic, okay? And then you have to know that when the optimal solution will change, when the optimal OFV will change. Okay, so there are quite a few combinations, right? Okay, so we also have some other examples or some other things you can use as exercise, okay? And you can certainly check it out. And we also have a summary of all the sensitivity analysis kind of main points, okay? Okay, so as far as the lecture is concerned, I will stop here. And okay, so so that's all for today's lecture. And but feel free to stay so you can work on these problems. If you have questions, you can ask me. Okay. So that's all.